Okay, so this lesson is on an introduction to reaction rates. So there's all kinds of different reactions out there that take all kinds of different amounts of time. When you're looking at the absorption of light, it takes fractions of seconds. Explosions are seconds, and the corrosion of something like a ship could take years, whereas weathering of rocks could take lifetimes. So there's lots of different rates of reactions, some very slow and some very fast. Now, if we were to look at some factors that influence the rate of reaction, concentration makes a big difference. For example, steel wool, when you burn it in regular air, what I mean by regular air is the stuff we breathe. Air is a mixture. It's only got 20% oxygen, and that's the specific component of air that steel wool is reacting with, and it occurs at a slower rate. It takes minutes to complete the reaction. Whereas if we were to take that same steel wool and put it in a 100% oxygen environment, it would burn at a much faster rate, and we would see this with a much brighter glow and a shorter amount of time spent burning to complete the reaction. So increasing concentration, obviously, is increasing the rate. So why is that? When I look at my particle representation of a reaction, it becomes quite clear. When I am having a reaction between particles, what's happening is those particles are colliding in just the right way with just the right amount of energy to produce a compound. If they don't collide perfectly, then they don't successfully produce a compound. So we've got an example of an unsuccessful collision and a successful collision. Our goal with a reaction is to have more successful collisions. So any factors that will increase the probability of a successful collision are going to increase the rate. So temperature is a measure of average kinetic energy, aka the speed of the particles. If my particles are moving faster, they're going to collide more frequently. Volume is really the space that my particles occupy. If there's less space, there's going to be more collisions. Pressure is a measure of the force of collisions over an area. If there's more forcible collisions occurring, there's probably going to be more successful collisions. Concentration is all about my amount of particles. If there are more particles present, there's probably going to be more particles colliding. Now, surface area isn't always the most obvious factor as to how it affects the rate of a collision or the rate of a reaction. So I've got a picture right here of sugar dissolving. It's a pretty common demonstration. You drop a sugar cube in water, and it's really difficult to not try to poke the sugar cube or try to stir the solution, because after a while of just sitting in the water, it appears that the sugar cube is no longer dissolving. It seems to be in the same state for a very long time. It's only upon poking or breaking the sugar cube that you start to see an increase in the rate of it dissolving. And that's because there are all of these particles of sugar within the cube that are not being exposed to the water. As soon as I break or poke this sugar cube and expose those interior particles to the water, I start to see my increased rate of dissolution. So increasing the exposure is increasing the surface area. So think about surface area as exposing particles to other particles. So let's talk about numerically how we might describe the rate of a reaction. Before I talk about reactions, I'm going to talk about an analogy. So Nathan's Hot Dogs has an annual hot dog eating contest. I've got some data right here for a general contestant. So this general contestant has 10 minutes to eat as many hot dogs as they can. So in the first 2 minutes, they consumed 15 total hot dogs. And then 4 minutes, 27, 37, 45, and 50. So it appears that they're consuming more and more hot dogs as they go on in time. But is that really an accurate description of what we'd see if we were there? Now, if we were there, you might be able to picture it. They start off strong, they're excited, they're hungry, they haven't eaten for a few days, but then as time goes on, you might see that they start to waver. They're not eating as fast as they were. They're possibly getting sick. Let's see if that reflects in this data. So at first, I consumed a total of 15 hot dogs from 0 to 2 minutes. So in a 2-minute window, 2-minute period, I consumed 15 hot dogs. Let's compare that to the end of the competition in my last 2-minute window from 8 to 10 minutes. In my last 2-minute window, how many hot dogs did this person consume? 5. That's a big difference. big difference. 5 hot dogs in 2 minutes versus 15 hot dogs in 2 minutes means that this contestant slowed down as they went through the competition. Now that seems fairly obvious, but having numerical data to back it up is always good as well. Now, my rate, if I want to describe the rate at which this person is eating hot dogs, it wasn't the blue values that I used. It was really the pink values that I used to talk about the rate at which this person was eating hot dogs. My pink values, oh, geez, I don't know why I put minutes right here. My pink values over here for my hot dogs, the plus 15 and the plus 5, this isn't the total number of hot dogs I've consumed. This is the change in the number of hot dogs I've consumed. So my plus 15 means that I changed the total number of hot dogs I consumed by 15. My plus 5 means I changed the total number of hot dogs I consumed by 5. So my other pink values, 2 minutes and 2 minutes, these are not moments in time. They're not reflected on the stopwatch. These are intervals. This is my change in time. So by comparing my change in hot dogs and my change in time, I get my rate at which I'm consuming hot dogs. So the rate for this hot dog eating contest is comparing your change in hot dogs to your change in time. Now, hopefully this is looking familiar to equations you've seen in math class, like change in y over change in x. This is a slope. It's a rate of change. Now for a reaction, we're not talking about individual particles like we would talk about individual hot dogs, because we work with quantities much, much larger. So instead of talking about individual particles, we talk about a concentration of particles. Now the units for concentration are molarity. Now molarity, just to refresh your memory, is moles per liter. And the unit of time we use to describe a reaction is usually seconds. So we can write our rate as molarity per second or moles per liter per second, whichever one makes more sense in that instance, but it's really the same units. Now let's look at a very simple example of a reaction rate. We've got chemical A becoming chemical B. We don't have to worry too much beyond that. Chemical A is becoming chemical B, and this image right here is giving us all of the data that we got in our table up above. It's giving us our time, it's giving us our amounts of A and B. The only thing it didn't give us is our volume, and the reason we need our volume is to figure out what's our molarity, because molarity is moles per liter. Now luckily the volume of these flasks is 1 liter, so our amount of moles is our concentration. So I took the liberty of rewriting my data over here in a little more organized way. At 0 seconds, my concentration of A is 1 molar. My concentration of B is 0 molar. At 20 seconds, my concentration of A is 0.54 molar, and my concentration of B is 0.46 molar. Now, if I wanted to describe the rate of this reaction, I'd have to figure out what's the change in concentration over the change in time. Now you might be thinking, well, I've got a lot of different concentrations here. What concentration are we talking about? Well, let's just compare. Let's figure out what's the rate in terms of B's concentrations and see what we get and if it makes sense. So to figure out my rate in regards to B, I need to figure out how much did my concentration of B change. So to find a rate of change, or to find a change, I should say, we take our final value minus our initial value. And then with time, we do the same thing, final time minus initial time. And this would get us 0.46 divided by 20, which when reduced is 0.023. Now our units are going to be molar per second. Now it makes sense that this is a positive value. Why? Because when I look at my concentrations, going from 0 seconds to 20 seconds, B increased its concentration by 0.46. So the rate should be positive in that respect because I'm increasing my molarity. Now for B, you might already be noticing that might not be the case because we're decreasing our concentration. So if I were to figure out my rate of A, I would do the same thing. My final concentration minus my initial concentration divided by my final time minus my initial time. And I'd end up getting negative 0.46 divided by 20. Now it's interesting, or I guess notable, that the number 0.46 is the same for A and B. The only difference is the sign. What this is saying is that when I lose 0.46 moles of A, that 0.46 moles is becoming 0.46 moles of B, and I'm getting that from this 1-to-1 ratio in my reaction. This is kind of like saying for every 1 atom of A, you're going to produce 1 atom of B. So now take that and multiply it by a scale of moles. So for my rate, if I were to simplify this, I'd get negative 0.023 molar per second. Now this creates kind of a confusing situation. Which rate do we use? Rate of B or rate of A? They're the same numerical value, however they're different signs. So think about it like speed. When I say it, I'm talking about rate. Think about rate like a speed. On your car's speedometer, you probably don't see negative speeds. Why? Because you're not really going negative distances. We can treat a reaction very similarly. We're not really going to have a negative rate because we're not having negative reactions. So for simplicity's sake, what we'll do whenever we have a rate that is negative is we will make it positive. And by doing, or the way to do that is by making that change negative, or multiplying our rate by a negative. Remember, a negative times a negative will yield a positive. So this is how I end up getting my rate for my reaction to be 0.023 molar per second. And I could have used either A's concentration or B's concentration, and I would have gotten the rate either way. So the rate of a reaction, or this one in particular, could be described as the rate of B or the negative rate of A. Now this is a simplistic equation with only one component becoming another component. So let's talk about an example that's slightly more complicated. So we've got this reaction right here up above. I've been given the rate at which oxygen is being produced, 9 times 10 to the negative 6 molar per second. I want to figure out what's the rate of nitrogen dioxide and what's the rate in regards to dinitrogen pentoxide. Now the way that I would do this is with a BCA table. BCA tables allow me to take advantage of those relationships with the coefficients, the mole ratios. So since we're talking about rates, a rate is usually a rate of change. So in my BCA table, the only row I'm really concerned with is the change row. I'm not really concerned with the before or after. I want to know how much is everything changing by. So I know that my oxygen is changing by 9 times 10 to the negative 6 molar per second. If I wanted to figure out my other components, how they're changing, I'd use my mole ratios. There's a 1-to-4 ratio between oxygen and nitrogen dioxide, which means that I need to multiply by a factor of 4 to get my rate that nitrogen dioxide is being produced. When I do this, I get 3.6 times 10 to the negative 5th molar per second. So that's simple enough. Now when I compare oxygen and dinitrogen pentoxide, I see there's a 1-to-2 ratio. So I've got to multiply my rate by 2. I've got to double it. So doubling it will get me 1.8 times 10 to the negative 5th molar per second. Now, once again, I'm only concerned with the change row because I'm looking at rates, which are rates of change. I don't care about my after or my before. So by looking at this, I have my rates for nitrogen dioxide and dinitrogen pentoxide. Now, the convenient part with the BCA table, you might be wondering, don't we normally consume reactants? So shouldn't this be a negative value? You are 100% right. It should be a negative value. We are consuming dinitrogen pentoxide. However, when we're describing the rate, we're going to make it a positive value. We're going to take the negative of that rate because we're going to describe reactions with positive rates. So for dinitrogen pentoxide, I can say that my rate is 1.8 times 10 to the negative 5th. And then for nitrogen dioxide, I could say it's 3.6 times 10 to the negative 5th molar per second. And what did I really do? I really just used these coefficients to figure that out. So what I essentially did was I said that, hey, my change in nitrogen dioxide over my change in time, this is what my rate is right here. My change in nitrogen dioxide divided by my change in time, this is equal to 4 times my change in oxygen divided by my change in time, which is exactly what I did right here in my BCA table. I multiplied by 4. I also did the same thing for my change in dinitrogen pentoxide. I looked at my coefficients and I said, this change in dinitrogen pentoxide is going to be double my change in oxygen per unit time because I had to multiply by 2. So if you like to use the coefficients and just do this computation down here, you're more than welcome to. Or if you'd like to use the BCA table, either way, you are more than welcome to do either of those options. So go ahead and try the next one, figuring out what is the rate in regards to oxygen and nitrogen dioxide. Okay, I'm assuming that you've attempted and that you've paused and unpaused the video and you're ready for a solution. So once again, I'm going to do this 2 ways with the BCA table and just by looking at the coefficients next. But let's start with the BCA table. So in my BCA table, I know that my change for nitrogen monoxide is 8.6 times 10 to the negative 6. I want to figure out how is my oxygen changing and how is my nitrogen dioxide changing. So this is a 2-to-2 ratio between nitrogen monoxide and nitrogen dioxide. So that means that they are really 1-to-1. So they are going to change at the same rate. Now, once again, nitrogen dioxide is a reactant, so I know it is being consumed, so this is technically a negative value. My oxygen compared to nitrogen monoxide is a 2-to-1 ratio. So what I'm essentially going to have to do is, instead of multiplying by a factor that's going to increase my rate, I need to multiply by a factor that's going to decrease it by 2, aka multiply by 1/2. 2 times 1/2 is what gets you 1. So I'm going to do the same thing with my rates right here. When I multiply by 1/2, I get 4.3 times 10 to the negative 6. So these are my rates that I could plug in over here. 4.3 times 10 to the negative 6 molar per second. And then for nitrogen dioxide, remember, we'll just use a positive value. 8.6 times 10 to the negative 6 molar per second. So now, if I wanted to just use my coefficients, I could have said, okay, my change in NO2 divided by my change in time. This is actually going to be the same as my change in NO over my change in time because there's a 1-to-1 ratio there. For my change in O2 though, my change in O2, since there's a 1-to-2 ratio and oxygen is half of my nitrogen monoxide, I would have to take my rate of change for nitrogen monoxide and multiply it by 1/2, which is exactly what I did in my BCA table. Now, working with the fraction is a little bit less intuitive than what we saw up above. So if you found that you had a hard time deducing that you had to multiply your nitrogen monoxide rate by 1/2 to get oxygen, but it was less confusing to do that in the BCA table, that might be a sign that the BCA table is a better tool for you. So hopefully this was clear, and let me know if you